Right now, there are galaxies moving away from us faster than the speed of light, and Einstein's rules don't stop it. They're gone. Unreachable. Forever. But here's what nobody tells you. The edge of the universe isn't a wall. It's not an ending. And buried inside our best physics equations, there are loopholes, real ones, not science fiction, that could change everything about what we think is possible. The universe is 13.8 billion years old. That part you probably know. But here's where it gets strange. The farthest light we can detect comes from objects that are now 46.5 billion light years away from us. Not 13.8 billion, 46.5 billion. That gap exists because space itself has been stretching the entire time that light was traveling toward us. The universe didn't wait around. It kept expanding while that ancient light made its journey. And by the time those photons finally reached us, the source had been carried billions of extra light years in the other direction. That 46.5 billion light-year bubble surrounding us, that's the observable universe. And it is all we will ever see. No matter how powerful our telescopes get, no matter how long we wait, no matter what we build. But observable doesn't mean all that exists. Out beyond that bubble, the universe almost certainly keeps going. Some models say it keeps going forever. Infinite space, infinite matter, infinite versions of everything, including, according to some physicists, infinite copies of you making slightly different choices right now. That's not a metaphor. It's a mathematical consequence of a truly infinite universe. The physics doesn't care whether it's comfortable. So what lives at the edge of what we can see? And more importantly, is there any way, even theoretically, to get past it? Let's start with the wall you can't punch through. Every point of light in the night sky reaches us because a photon traveled across space and hit your eye or your telescope's sensor. Simple enough, but there's a moment in cosmic history when light itself was completely trapped. For the first 380,000 years after the Big Bang, the entire universe was a dense, roiling plasma, a fog so thick that photons couldn't travel more than a tiny distance before slamming into charged particles. Light had nowhere to go. The universe was opaque. Then the temperature dropped enough for electrons to bond with protons and form neutral hydrogen atoms. Suddenly, the fog lifted. Photons streamed free in all directions, and the universe became transparent for the first time. That moment, 380,000 years after the Big Bang, is the absolute limit of what any telescope can ever observe. Not because our technology isn't good enough, because before that moment, no light existed that could carry information to us. That ancient flash of freed photons is still traveling through space today, stretched by 13.8 billion years of expansion into the microwave range. We call it the cosmic microwave background. It's a faint glow of 2.7 degrees above absolute zero that surrounds us in every direction, the oldest light in existence, and it is a wall, a literal boundary. Look past it, and you're looking into a time when looking wasn't physically possible. The universe was born opaque, and for everything that happened before those first 380,000 years, we can never have direct optical evidence. Now here's where it gets weirder. Beyond our observable bubble, past the 46.5 billion light-year edge, space is still expanding, and at around 14 billion light-years out, something crosses a threshold. The recession speed of galaxies at that distance matches the speed of light. That boundary is called the Hubble sphere. Everything beyond it is moving away from us faster than light. Before you say, but nothing can travel faster than light, that rule applies to objects moving through space. Space itself has no such speed limit. It can expand at any rate it wants, and in the outer regions of the universe, it absolutely does. Those galaxies aren't violating Einstein. They're just being carried outward by the metric expansion of space, the way raisins in rising bread dough move apart without any raisin moving through the dough itself. What that means practically is staggering. There are regions of the universe that emitted light toward us billions of years ago, light that is right now in mid-journey, that will never reach us. Space is expanding faster than the photons can close the gap. They've been racing toward Earth their entire existence, and they'll lose the race. That information is gone. Those galaxies might as well be in another universe entirely. And yet somehow, we know something is out there. We feel it. Our galaxy, the Milky Way, is moving. Not just drifting from the Big Bang's initial push, actually accelerating toward something. The The Milky Way, along with the entire local group of galaxies, is being pulled at 1.4 million miles per hour toward a point in space we call the Great Attractor. That's not a name cosmologists invented for drama. It's a region of intergalactic space, roughly 150 to 250 million light-years away, that is exerting a gravitational pull so massive it's tugging on hundreds of thousands of galaxies simultaneously. Here's the problem. We can't see it directly. The Great Attractor sits almost perfectly behind the densest part of our own galaxy, the Milky Way's galactic plane, a thick band of stars and dust and gas that blocks our line of sight in that direction. Astronomers call it the zone of avoidance. Invisible light, it's completely blocked. You can't look through the Milky Way to what lies behind it, any more than you can look through a concrete wall. Radio waves and X-rays pierce some of that veil. And what researchers found when they looked was a massive concentration of galaxies. The Norma cluster sits at the heart of the Great Attractor region. But that's not even the end of the story. Only about 44% of our galaxy's motion comes from the Great Attractor itself. The rest is pulled from even deeper, from an enormous structure called the Shapley supercluster. 500 million light-years away, the most massive concentration of galaxies identified in the observable universe. Something is pulling, and something behind that is pulling harder. We are being reeled in by forces we can barely see, toward objects we can't fully map, across distances our brains weren't designed to hold. Now picture something even emptier. In 1981, astronomer Robert Kirshner was mapping the large-scale structure of the universe, cataloging which regions had galaxies and which didn't. What his team found in the constellation Boötes stopped them cold. A region of space roughly 330 million light-years across, with almost nothing in it. 60 galaxies where there should be around 2,000. A void so enormous that if the Milky Way sat at one edge of it, the other edge would be so far away that the light leaving it right now wouldn't reach us for hundreds of millions of years. Astronomers named it the Boötes void, and it still ranks among the largest known structures in the observable universe. Except it's a structure defined by absence. Why would the universe leave a hole that big? The answer goes back to the first fraction of a second after the Big Bang. Matter wasn't distributed perfectly evenly. Tiny quantum fluctuations created microscopic patches that were just slightly denser than their surroundings. Those denser patches had slightly stronger gravity. They pulled matter in from their neighboring regions, making themselves denser still and leaving the regions they drained increasingly empty. Over billions of years, that feedback loop built the cosmic web, a lace of galaxy filaments and clusters, threaded through with vast voids. The Boötes void is one of those stripped-out regions, a casualty of 13 billion years of matter flowing toward concentrated gravitational mass. And in 2015, researchers found something even larger, a void measuring 1.8 billion light-years across. The universe is mostly empty. About 80% of its total volume is void. The galaxies and clusters we observe are concentrated in a thin, delicate web threading through seas of nothing. Here's the question that keeps physicists up at night. Given all of this, the speed limits, the expanding void, the unreachable edges, is there any way out? Not the fantasy version. The real physics version. In 1994, a physicist named Miguel Alcubierre was playing with the math of general relativity when he found something remarkable. He constructed a solution to Einstein's field equations, the same equations that describe black holes, gravity waves, and the expansion of the universe, that described a spacecraft inside a bubble of flat space-time. Behind the bubble, space contracts. Ahead of it, space expands. The ship doesn't move through space at all. The space around it moves. And if you can do that, you're not bound by the speed of light. This is the Alcubierre drive. It's not science fiction, it's a legitimate mathematical structure that general relativity allows. The problem is making it real. The drive requires something called exotic matter, a material with negative energy density. We've never created it in bulk. The Casimir effect, a quantum phenomenon where two metal plates held close together experience an attractive force, gives us hints that negative energy states exist in nature. But the amount of exotic matter needed to power a functional warp bubble, by early estimates, was equivalent to the mass energy of an entire planet, or larger. Some calculations pushed it towards stellar mass. More recent work has tried to bring that number down. Physicists Harold White and others have proposed modified versions of the original Alcubierre design that reduce the energy requirements significantly. The math isn't settled, but no, one has proven the concept is impossible, only that we don't yet know how to do it. Wormholes live in the same neighborhood of physics. An Einstein-Rosen bridge, the technical name for a wormhole, appears naturally as a solution to general relativity's equations. Two distant points in spacetime connected by a tunnel through curved space. Fold the map and punch a hole through it. Walk out the other side somewhere else, entirely. The catch? The same one. A traversable wormhole, one you could actually send a probe or person through without it collapsing, requires exotic matter to hold the throat open. Without it, the tunnel pinches shut almost instantly, faster than anything could pass through. Recent simulations in 2023 confirmed that even in quantum systems with entangled particles, the wormhole throat closes before any causal signal gets through. There's a concept in modern physics called ER equals EPR that might change this picture. The idea, proposed by physicists Juan Maldacena and Leonard Susskind, is that quantum entanglement, when two particles become linked so that measuring one instantly affects the other, is actually the same thing as a microscopic Einstein-Rosen bridge. Every entangled pair in the universe is, in this framework, connected by a wormhole. That's not proven, it's a conjecture, but if it holds, it reframes the structure of space-time at a fundamental level. None of this works tomorrow, but all of it is real physics. None of it is fiction. And here's what matters about that. Every hard limit in the history of exploration was called permanent right up until someone found the loophole. The atom was considered indivisible until it wasn't. The sound barrier was a wall until it wasn't. Flight was impossible until it happened twice in a field in North Carolina in 1903, and the world had to update its understanding of what impossible meant. The observable universe's edge isn't a wall built to keep us out. It's a horizon, a limit defined by the current state of our physics, our technology, and our knowledge. Horizons move as you approach them. They always have. We sit right now at the edge of what we can see, watching galaxies vanish past our cosmic horizon forever, being pulled at 1.4 million miles per hour towards something half hidden by our own galaxy's bulk, surrounded on all sides by the faint glow of the oldest light that exists, and buried in our equations that have been right about black holes, gravitational waves, and the expansion of the universe itself. There are doors, not open doors, not easy doors, doors that may require materials we've never produced, energies we've never tapped, and ideas we haven't had yet. But they're there. So let me ask you this. If we ever find a way to step outside the observable universe, to cross that boundary and see what's actually out there, should we? Because some physicists argue that what we'd find past the edge might shatter every model we've built about where we came from. And next week, we're going into exactly that. The theories about what the universe looks like from the outside, and why the answer might be nothing like any cosmologist predicted. Drop your answer in the comments. Do you think humanity will ever break past the observable horizon, or is that a boundary we're permanently stuck behind? I read everything down there. If this broke your brain a little, hit the like button. It genuinely helps the channel get these ideas in front of more people. Share it with someone who thinks the universe ends at the stars they can see. And make sure you're subscribed, because next week, we go somewhere even stranger. The universe isn't done surprising us, and neither are we.